Welcome back. In this module, we're going to cover industrial networking. And what we're going to focus on is what is needed to pass the CSE exam and to be familiar with networking for the CCST exam. We're going to focus on the CSE and what was required in the specifications from the NCEES. And we're going to work our way up into control networks, and we'll see how a control network works and what it uses and the difference between TCP and UDP as used in TCP IP in industrial networks. As far as control networks, I'm not going to talk much about that, just a little bit to show you what it is. If you go to the Control Systems Engineering Exam Reference Manual, Practical Study Guide, we have a whole section on that, and there'll be 16 pages just on control networks, and so you can look at that. So we're going to focus on Ethernet and industrial Ethernet, and we're going to focus on UDP, User Datagram Protocol, and TCP, Transmission Control Protocol, and we're going to show how to use these with controllers. And we're going to talk a little bit about OPC, and we're going to talk about baud rate and bits and error checking used with industrial PLCs for serial communications. And, well, I guess that's good enough. Let's get started. Okay, we've covered just about everything we need on the CSE exam. Remember, on the CSE exam, networking will be up to 8 questions. So this is a significant amount of questions. So we need to pay attention to this networking. Plus, everyone today is using networking and control. And it's jumping up everywhere you go, so you need to be familiar with this. And on the CCST, there'll also be a little bit of networking, troubleshooting, understanding how networks work. But in control networks, we don't want to use dynamic host connection protocol. Typically, we want to use a static IP address. And when you're building a machine and a machine and a machine, you would like them all to be the same when you build them. So typically, they might build these with the same IP addresses for the same hardware. And then what we can do is go through these switches, and these industrial switches will do network address translation. And so we might have 192.168.1.1 on this side, but as you're looking here at the Rockwell diagram, looking on the left, the 191.168.1.1 would be translated to 10.10.10.1. And so we might have 192.168.1.3 for one of these Ethernet adapters at the bottom on the left. But when we get out of the network, it would be 10.10.10.3. And this allows us to route between our networks. And so on the other side, even though we got a 192.168.1.1 and a 1.3, it'd be translated to a 10.10.20.1 and a 10.10.20.3. And it would be routed through the layer 3 switch. This allows for us to have a network made as a prototype and duplicated over and over. And then when we connect it into bigger networks and these machines are connected together, we can use network address translation to give them another address to the rest of the network to communicate between them. Okay, another thing is on time critical type applications. We don't use TCP. We'll use what's called UDP because it's smaller and it has less overhead and it's faster. And you say, well, what's the difference? Well, we're going to explain that in a second, but instead of worrying about did you receive the package, just like talking on a cell phone and you're FaceTiming, you don't care if you missed one image because you're going to miss more images. It's going to be delayed. So we just keep on going and we catch the next image. On critical process control, you don't care if you missed a glitch in an analog readout. You just get the next analog readout. And this is where UDP is faster and is used for a critical process. So let's take a look at UDP and TCP and see what the difference is and why we use these.
In this video, we'll cover the two major transport protocols, UDP and TCP. Before we do that though, let's talk about transport protocols in general to understand why we need them in the first place. On the internet, every network packet follows this 5-layer structure. We have the application layer, the transport layer, the network layer, the link layer, and the physical layer. But for now, just remember that UDP and TCP are part of the transport layer. Have you ever wondered why it's possible that two applications can use the same internet connection at the same time? Well, that's because of what the transport layer provides. It allows multiple applications to use one network connection simultaneously. Much like street names have house numbers, the transport layer creates about 65,000 ports on your computer per network connection. These ports can be reserved and used by applications on your computer, and one application can use multiple ports at the same time if it wants. Let's say that an application reserved port 12437 to send a message to port 80 on some other machine. Whenever the application layer creates a message, it is passed on to the transport layer. On this layer, we wrap the message inside what we call a segment. This segment contains some additional information like the source port as well as the destination port. Then, when the segment is created, it is passed on to the network layer for further processing. Our segment will show up on the receiver side when it is passed on from its network layer to the transport layer. The segment will be examined to determine the destination port, and then the message is unwrapped and delivered to port 80. So that's the general idea of the transport layer, but there's more to it than that. We have two major transport protocols, UDP and TCP, and they both have their own characteristics. Let's look at UDP first. One of the biggest advantages of UDP is that its packet sizes are smaller than TCP, about 60% even. UDP headers are 8 bytes and TCP headers are 20 bytes, so that's a big difference. UDP is connectionless. This means that you don't have to create a connection first before sending out data. And finally, you have more control over when data is being sent out. Now, I do realize that this may sound a little vague to you, but once we get TCP into the mix, this will become clearer. Because data corruption is a common occurrence on the internet, UDP has a primitive form of error detection. Its packets carry a 16-bit checksum, but it is not that reliable. When UDP does detect corruption, it will not try to recover from it. In most cases, the corrupted segment will just be discarded. In some cases, it will keep the corrupted segment, but turn on a warning flag for the application. UDP does not attempt to compensate for lost packets. Every packet gets sent out once. If it gets dropped on its way to the receiver, tough luck, it's gone. UDP does not guarantee in-order packet delivery. Packets won't necessarily arrive in the application in the order that they were sent. There's no congestion control in UDP. Even if your network's really busy, UDP will just try to cram those packets in there. This is usually a bad strategy because on a congested network, packets get dropped more often. In conclusion, UDP may be lightweight, but it's not that reliable. This is where TCP comes in. The Transmission Control Protocol has certain features that make it more reliable than UDP. However, it also has a bigger communication overhead than UDP. Since TCP is connection-based, we have to negotiate a connection first before we can do anything. This procedure is known as a three-way handshake. First, the initiator will ask the acceptor if it wants to set up a connection. The acceptor will reply to this request, and when the initiator receives this reply, it will send a packet to the acceptor that acknowledges that the connection has now been established. A similar song and dance takes place when they close down a connection. Now that we have this connection, we can implement all kinds of nice features like delivery acknowledgements. When data gets sent from one host to another, the receiver will acknowledge that it got that data. This is one of the reasons why TCP segments carry a number. Another feature that TCP offers is retransmission. When a sender doesn't get a delivery acknowledgement within a certain amount of time, it will assume that the packet got lost on its way, so it will send it again. Because segments are numbered in TCP, it can also implement in-order delivery. Although packets may still arrive out of order, TCP will rearrange them before sending them to the application. Other TCP enhancements include congestion control. This feature will delay transmission of data when the network is congested. It eases the strain on the network and it helps minimize packet loss. TCP enforces a small change to error detection. While there is no technical improvement of the error detection feature, the checksum has now been made mandatory for IPv4 as well as IPv6. For UDP segments, the checksum is only mandatory for IPv6 packets. Let's look at the downsides of using TCP. TCP segments need bigger headers than UDP segments. As you may remember, UDP headers are about 60% smaller than TCP headers. A side effect of TCP's congestion control mechanism is that data doesn't always get sent out immediately. This is of course done on purpose to ease network congestion, but sometimes that's not what you want. Take Skype for example. When you're making a voice call, you kinda want it to feel like a real-time conversation, right? Well, what TCP's congestion control does is when the network is congested, it deliberately introduces latency, so your real-time conversation will not feel as real-time as you want it to be. As you can see, congestion control can be either a nuisance or an enhancement. It all depends on the context, really. Finally, TCP has a bigger overhead. All those retransmissions and packet acknowledgements and all that jazz, well, that's overhead. Sometimes you don't want every packet to arrive. Sure, you want packets to arrive, but if certain packets drop out, you don't care that much. For example, to stream HD video, you need lots of bandwidth, but if you use TCP for it, you need even more because you have to send around acknowledgements, you have to do retransmissions, and besides, video streaming can deal with a certain amount of packet loss. They have ways to compensate for that. In this case, it makes more sense to use UDP than TCP. Both protocols are also different on a conceptual level. We call UDP message-oriented, which means that applications send their data in distinct chunks. Think of it as snail mail, email, or text messaging. Now TCP, on the other hand, is stream-oriented. It is used as a continuous flow of data. Under TCP, your application does not choose how data is sliced into packets. Just let it know whenever anything needs to be sent, and then TCP will slice that into packets and recompose everything on the other end. It could use lots of small packets, but it could also choose to go with few big packets. It just picks whatever works best at that time. Rest assured though, you don't have to worry about how the packets are sliced. All you need to know is that on the receiver end, everything gets recomposed into a stream that you can read from. So which one's better, UDP or TCP? It all depends on the type of application that you're building. Let's look at text communication. Performance-wise, this isn't a big challenge because you don't need a lot of bandwidth to send some text around after all. Under TCP, everything will work fine. With UDP, however, you could get text in the wrong order or text could get lost along the way. There's no guarantee. Anything could go wrong there because UDP doesn't do retransmissions and it doesn't guarantee in-order delivery. When it comes to text communication, TCP clearly takes the cake. Now, I don't know about you, but when I download files off the internet, I'd like to have all the parts, including the chunks that didn't make it through the first time. TCP offers retransmission, UDP does not. We're also going to need in-order delivery because seriously, what good is a scrambled JPEG? For similar reasons, remote access protocols like SSH also use TCP. If you need delivery acknowledgements, UDP isn't going to do you any good. If you insist on using UDP, you could implement some sort of acknowledgement system in your application layer for important packets, but most of the time it's not worth the hassle. With multimedia streaming, things are a little more ambiguous. It could either be UDP or TCP. Traditionally, people have chosen UDP because it has less overhead, it doesn't do that congestion control thing that introduces latency, and we can compensate for a certain percentage of lost packets. More recently, people have started to use TCP for multimedia streaming. If the bandwidth is there, you might as well enjoy the benefits that TCP brings. Also, some firewalls block UDP altogether for security reasons, and then you're forced to use TCP. UDP can also be used for small question and answer transactions, such as DNS lookups. The main benefit here is that you don't have the overhead of creating and closing a connection every time you need something. As is the case with multimedia streaming, bandwidth-intensive apps that can tolerate some amount of packet loss usually go with UDP.
So we can see here from this diagram, anything using Ethernet IP basically is the same thing, whether using Rockwell or whoever. We use TCP for like messaging. Say I want to send a message. Say I got a bunch of data and I want to send it to another PLC. Well, I use TCP IP to make sure it does actually get that message and it's correct and all the data is there. But if you look at the bottom of this here, you'll see UDP. And when you connect to the I/O adapter, not always you have to pick this, but typically you'll pick what's called implicit messaging. And this uses UDP, and it's so fast, it appears as if it's local I/O to the PLC. Even though you got a remote adapter, like with the control logics, it'll appear in your tags just as if it's local I/O. But for speed, we use UDP. And if we miss a piece of data, it's not a big deal. We'll get it the next scan. But when we're transferring like a count of how many parts or how many pieces have been put out, or if we're keeping the names and tracking names or data, we need TCP, which is explicit messaging, to make sure we get every piece of data and it is correct. Okay, one last thing is we need to look at firewalls and ports. If we don't have these ports open in our firewalls, these firewalls that are protect us, we can't communicate. And we need to talk about security and hardening. When they say hardening the system, or when you harden the network, this means you make it more secure as you can. This means by turning off unused ports so people can't plug in, maybe verifying that only a machine with that particular MAC address can talk so other people can't plug in other machines. And this also works on your wireless networks as well. You can keep certain PLCs out and only certain PLCs get in. Matter of fact, when you're setting up a workgroup bridge, you'll use the MAC address of the workgroup bridge and it will go into the access point so it knows where it's coming from. In other words, who the access point is talking to, and it is really the workgroup bridge. And then the workgroup bridge will have the MAC address of the access point, so it knows it's only that access point that it's talking to. This helps to provide security, and it gives us a path to go back and forth with our communications. Now remember, just like gateways, there's two ports. There's a software port, which is a number used in the IP address that says what piece of software goes where and what can communicate with it. And there's a hardware port, which is where you plug in your Ethernet cables in the hardware of the switches and the routers. So be sure to understand the distinction between the two. Okay, let's look at firewalls.
Let's talk about firewalls. Firewalls are absolutely critical on today's computer systems. There was a time a long time ago when we just didn't think much about firewalls, but today, with all the threats that present themselves from a public network, you must have a firewall installed on your system. Let's talk about what a firewall is and how it works. A firewall is either a piece of hardware or a piece of software or a combination of both, depending on which type of firewall you're using and how you're implementing it, that sits between your network and a public network, such as the internet. We have our systems over here on our network. Then we have the great cloud of the internet. We need a means of protecting our network over here and our host systems, we'll label this internal, from this external network where chaos rules. If we did not implement some kind of barrier between these two, then anybody on the internet could find their way onto our internal network and could do all kinds of things. They could compromise data, they could steal data, they could bring systems down, all kinds of things. You don't want that kind of thing to happen. Let's spend a little more time looking at how a firewall works. When we implement a firewall on a network, what we do is we place a system between our internal network and our external network. All the data that passes through this system is examined based on a set of rules that we define that determine whether or not that traffic is allowed. By doing that, we have erected a firewall between our network and the external network. In other words, we could say any data that originated outside the network that's trying to come in, do not allow. We say, no, you cannot come inside. We can say any data that originated with a request from the internal network. For instance, if somebody said, I want to get this web page from this web server, we can say, okay, let's go ahead and allow that. We can say any FTP traffic coming through is not allowed because we don't want passwords and usernames being transmitted clear text. We can say data that's being transmitted on a particular port, such as port 80, is allowed through the firewall, but any other data is not allowed through the firewall if it's running on a different port. As you start working with firewalls, you will soon see that there are many different types of firewalls that you can implement. Let's first look at the difference between a network firewall and a host-based firewall. With a network firewall, we take a firewall device, it could even be a computer running firewall software, and we install two interfaces in it. One network interface connects to our internal network, one network interface connects to our external network or to the internet. All data going to and from the internet, it goes through the firewall and it uses the rules that we specified to decide whether or not traffic is allowed through or whether traffic is not allowed through. That is a network-based firewall. All networks that connect to the internet they must have some type of firewall. In fact, most folks who implement firewalls for a living recommend that you do layered firewalls. You don't use just one, because if a hacker manages to find his way through the one firewall, they got full access to your network. They recommend installing layers of firewalls so that if a hacker gets through one, all of a sudden he's got another one he's got to get through, and another one. In other words, making it not worth the effort. You know, go on and find some other network that's only got one firewall instead of wasting your time with this one. However, it is also possible to have a host-based firewall. With a host-based firewall, we have a single system that is connected to the internet. And it doesn't matter how it's connected. It could be connected via a modem. It could be connected through a network. It could be connected through a DSL line. It could be connected through a cable modem. However it is connected, it does have access to the internet. However, instead of installing a firewall somewhere over here between the system and the internet, you have software installed on the system that operates as a firewall for that one particular host only. Now, a network firewall examines all traffic going to and from the internal network and deciding whether it's allowed or not. With a host-based firewall, we examine all traffic coming to and from just this one host and deciding whether or not it's allowed. Now, these two are not exclusive. In fact, most of the time when you're dealing with an organization, you will probably be running a host-based firewall on each machine. It comes with Windows XP. It's really nice. And you'll also be running a network-based firewall up here. Firewalls are absolutely critical. If your organization doesn't have one on its network, or if you don't have host-based firewalls running on each individual system, you should crank it up and get it going, because without them, your systems are subject to serious security threats. That's it for this lesson. In this lesson, we talked about using firewalls to protect your network.
Okay, even if you're using a hardware firewall, you still have to allow the software ports to be opened on the computer. So say you had an HMI server or a licensed server or something like this, and the PLCs are trying to communicate to the server. You have to make sure these ports are opened in your software security of your firewall on the individual computer. It's not just an outside firewall. So it's important that your host-based firewall have these ports open. Typically, they're opened automatically when the software installs if you install it as an administrator, but not always. So be sure to verify that. Here we're looking at the Rockwell Cisco typical plant. And we're seeing the enterprise level, and then we see the email, internet, and business in the gray. And then we see the demilitarized zone. And this is where we redirect certain applications. These are where our servers will be basically, and they're protected. And next we have our manufacturing zone, and then we have our cell area zone. And this is where we have our supervisory control, and this will be our factory talk clients and our operator interfaces. Your engineering workstations are typically in the manufacturing zone. So we have a firewall for the enterprise coming in, and we also have a firewall between our demilitarized zone and our manufacturing zone. And we keep the corporate and the manufacturing separate. Typically we want a firewall between those two. You'll see at the bottom we have our batch control, discrete control, drive control, continuous control. These will be our PLCs on the level 1. And then we have our actual devices, our sensors, drives, actuators, robots, and this is the process level. Here we're looking at some of the most popular industrial networks. And you see from the bit level on the lower left to the megabyte of data exchange on the lower right, and you'll see your response time of how long it takes coming up. So as you see, Ethernet, TCP/IP, this could be like PROFINET or Ethernet IP or EtherCAT. These are very fast networks, and they respond very quickly, and they handle megabytes of data. While if you're looking at Profibus DP, we're in the bytes, and if we're looking at DeviceNet, we're into the bytes of data being transferred. And you'll see Profibus PA can go from the bit level clear up to the byte level. And what's important is this is the amount of data you're exchanging, or what they call the bandwidth. How much data are you trying to put through in a few seconds? And this is called the baud rate, bits per second. And so typically we use 1024 bits per second will be 1 kbaud. So when they're talking about bandwidth, they're talking about how much data does it put through per time. And you want to be familiar with distance versus length. They may have something like Ethernet, and they'll say, what is the distance Ethernet can go without being repeated and needing a repeater? And that would be 330 feet or 100 meters. Typically, your Ethernet only goes up 100 meters without a repeater. And a repeater can be a switch or a router. Either one will repeat the signal and restructure the signal. So next is fiber, and fiber is called FDDI. And this stands for Fiber Distributive Data Interface. And with fiber, there's different topologies, but typically we just use a linear type topology. And with the fiber, you can get up to the gigabits of data easily. There's not much problem there. But fiber optics, when we use fiber optics, we can go miles with fiber optics. And they may ask something about the reflective index. Some fiber optic cables have a single index, which means the light can bounce back and forth on the edges, goes down through there. And when it gets to the end, if you go any long distances, you're out of sync because you have bits in the middle that are traveling faster than the bits that were going on the outside, and they shift and you get corrupted data. So they can have a reflective index, a variable index cables, and it's denser in the center than it is on the outside. That way the light travels slower in the middle than it does on the outside, and they typically reach the same time if you go long distances. So be familiar with that for your exam. So you prefer to use a multi-mode graded index or a single mode step index to get your best signal over long distances. Okay, now is a good time for a break. Maybe do some review if you want. When we come back, we'll talk about industrial Ethernet control networks, PROFINET, Ethernet IP, Modbus TCP IP, and we'll talk about industrial switches and how to set up these industrial switches for the basic setup, and we'll discuss some more terms used on the exam that you need to be familiar with. There'll be a couple of videos on OPC, Object Linking Embedding for Process Control, as an introduction. And that'll wrap up our industrial networking. That'll be it for this module. So here we go. Okay, when we're using Ethernet in industrial networks, it's only about 13, 15 years old. They haven't been used very long because they were not what's called deterministic. And in a control network, it has to be deterministic. That means that when we send our packets, they have to arrive within a certain time. And typically this is done by scheduling the traffic between your controllers and your I/O. And so what we're going to do here is take a look at a film on industrial Ethernet protocols. We're going to look at Modbus, PROFINET, and we're going to look at Ethernet IP. And we're going to see how these exactly work in the control network environment and timing. Okay, let's take a look at it.
Just as in the enterprise IT environment, having communication standards and standards organizations is necessary. These same requirements exist in the industrial networking environment. A variety of communication standards are used at all levels to control the mining process in the mining network. These standards are similar to the same ones used in oil and gas industry networks. The communication standards and protocols used include PROFINET, provides a fast and reliable way to access powerful diagnostic information and troubleshoot issues quickly. Profibus links control systems with field devices such as sensors and actuators. This protocol enables a consistent data exchange with higher ranking communication systems, which supports the automated mining process as well as in-motion control and safety-related tasks. Modbus, a serial communications protocol which is often used in connecting industrial electronic devices. Modbus enables communication for up to 240 devices on the same network. Modbus is commonly used to connect a remote terminal unit, or RTU, with supervisory control and data acquisition, SCADA, systems. Some mines have introduced Modbus TCP to take advantage of cost-efficient Ethernet network cards, switches, routers, and cabling. And lastly, Ethernet IP. Used together with CIP sync and CIP motion technologies, it enables real-time control for motion control applications. PROFINET is one of the multi-bus Ethernet-based standards for the automation industry. This standard allows integration with IT and field bus systems. PROFINET input-output supports real-time automation and is built on Ethernet and TCP/IP standards. There are 3 different implementation versions of PROFINET, each of which has been optimized for different applications. Some implement non-standard protocols, other versions do not use the TCP/IP layers included in the architecture. The 3 protocol levels defined for PROFINET include PROFINET TCP/IP. PROFINET TCP/IP is used for non-deterministic functions such as parameterization, video and audio transmissions, and data transfer to higher-level IT systems. PROFINET RT. The TCP/IP layers are bypassed in order to give deterministic performance for automation applications in the 1 to 10 millisecond range. This ability represents a software-based solution suitable for typical input-output applications, including motion control and high-performance requirements. PROFINET Asynchronous Real-Time, or IRT. At this level, signal prioritization and scheduled switching deliver high-precision synchronization for applications such as motion control. Cycle rates in the sub-millisecond range are possible with jitter in the sub-microsecond range. This service requires hardware support in the form of readily available ASICs. In each of these implementations, PROFINET protocol does some portion of the OSI model function. Modbus is a serial communications protocol originally published by Modicon for use with its programmable logical controllers, or PLCs. It is an open master-slave protocol that can be used, for example, from PLC to an input-output device. Modbus is common in an industrial system because it allows the master to transmit messages that are picked up by multiple slave devices on the same segment. Modbus TCP/IP, also Modbus TCP, is simply the Modbus RTU protocol with a TCP interface, which runs on Ethernet. In this figure, the Modbus TCP master can either wait for each response to return before the next request is issued, or it can send several requests at once in order to allow for parallel processing in the slave devices. In the latter case, the overall performance is improved. The Modbus protocol is still in use in the automation world because Modbus can connect IP Ethernet networks. The main change in the modern network is that Modbus now uses TCP/IP as a transmitting protocol. Another change is that instead of having one master and multiple slaves, Modbus now supports a client and server architecture. For example, HMIs or PLCs would be clients, while input-output racks would be considered servers. Significantly, Modbus is no longer limited to one master with a number of slaves. Instead, any number of clients can access any number of servers. A Modbus TCP/IP application data unit, or ADU, consists of the traditional Modbus Protocol data unit, which is also present in the Modbus over serial line method, and a new Modbus Application Protocol header, shortly MBAP. The function code and data definitions of Modbus Protocol data unit remain intact. TCP uses registered port 502 to send Modbus application data units through the TCP/IP network. Modbus will continue to be popular for simplicity and the fact that there are many users with Modbus knowledge in the field. Additional architectures and protocols used in the industrial environment include data exchange protocol models such as Common Industrial Protocol, or CIP suite. CIP is an information exchange protocol for industrial automation applications. CIP allows users to integrate manufacturing applications with enterprise-level Ethernet networks and the Internet. CIP is a messaging protocol that defines how different industrial automation and control system network devices, systems and applications come together to form an application. Similar to the application protocols in the TCP/IP protocol suite, CIP encompasses a comprehensive suite of messages and services for the collection of manufacturing automation applications. Those applications often include control, safety, synchronization, motion, configuration, and information systems. CIP exists on OSI layers 5 to 7 and is a single media-independent platform that can be used across 4 layers: sensor and actuator layer, device layer, controller layer, and the Internet layer. The 4 network adaptations of CIP that are available include CompoNet. On the sensor and actuator level is an ODVA network. It's not as common as the other 3, but CompoNet is a networking solution for the sensor and actuator layer of components. DeviceNet, which is on the device layer and was the first public implementation of CIP. DeviceNet employs a controller area network, or CAN, in data link. ControlNet, which lies on the controller layer. It is a deterministic digital communications network that provides high-speed transport of time-critical input-output and messaging data. ControlNet uses concurrent time domain multiple access, or CTDMA, in its data link layer for bus access. And lastly, Ethernet Industrial Protocol, or Ethernet IP, which is on the Internet layer, and it's the widely accepted industrial Ethernet network solution available for manufacturing automation. The important aspects of the CIP implementation of Ethernet IP are the various types of messaging that are used and how the types are implemented in standard Ethernet TCP/IP. All connections in a CIP network can be divided into unconnected messaging, explicit messaging connections, and implicit or input-output messaging connections. Unconnected messaging in the CIP protocol is used to open a non-time critical CIP connection with another device. Explicit messaging connections provide generic multi-purpose communication paths between two devices. Explicit messages provide typical request and response oriented network communication and are always made to the message router object. Each request contains explicit information that the receiving node decodes, acts upon, and then generates an appropriate response. Implicit messaging connections provide dedicated special purpose communication paths or ports between a producing application object and one or more consuming application objects. This type of messaging is always used for application-specific input-output data that moves through these ports, and so the messaging is often referred to as I/O connections. The messages are called implicit messages because the data is identified at the time that the connection is established and connection IDs are assigned. Again, we can see similarities between this environment and the TCP/IP environment used for data exchanges in non-industrial networks.
Okay, let's take a quick look at object linking and embedding for process control, OPC, and see what some of the common terminology and uses are and how we utilize this for the exam.
In our fast-moving, data-driven world of 21st century industrial automation, continuous real-time communication is vital between people, between systems, between technologies. It's this kind of connectivity that helps manufacturers produce world-class products, saving time, motion, and dollars, expediting return on investment. In years past, this wasn't the case. Automation and supporting enterprise systems couldn't talk to one another without expensive custom solutions. Integrating diverse proprietary technologies required vendors to develop numerous communications drivers or repair existing ones. Costly efforts for everyone. What manufacturing plants really needed was interoperability with more freedom of choice. In 1996, a group of leading worldwide automation suppliers collaborated to solve these issues and streamline the industry. What resulted was the OPC Foundation and OPC, Open Connectivity via Open Standards. For the first time, the marketplace could build best-of-breed systems, where generic OPC clients like HMI SCADAs from one vendor could easily consume data from any of the OPC Foundation members' servers. OPC is an exciting, enabling technology that has led to improved cooperation between technology providers and users. It offers a long-awaited published industrial standard for system interoperability based on Microsoft technology. OPC is based on a client-server technology. The client allows a user to make read-write requests to an OPC server, which then translates items into device protocol-specific requests that the underlying machinery understands. Here's an everyday example. Think of the client as a patron in a restaurant. He comes in, selects what he wants from the menu, and places his order with a server. The server then takes the order to the chef in the kitchen, who prepares it and has the server deliver the requested meal to the patron. Similarly, an OPC client makes a request from an OPC server. Let's say, what's the value of FC10101? The server then polls the device for the value and delivers it to the client. It sounds simple, but it took some great minds to simplify what was once a complex and costly data access problem. Some of the core standardized specifications OPC Foundation members came up with include OPC Data Access Specifications, which provide real-time data access, a timestamp, and a quality code for each value requested. OPC Historical Data Access, HDA, which can be used to retrieve and analyze historical data and enable analysis, trending, and reporting. The HDA typically retrieves data from a historian or relational database. OPC Alarms and Events, A&E, which provides real-time OPC alarm data where rules can be configured for determining when a point goes into an alarm state and the level of information to be made available when an alarm is raised. Today, the OPC Foundation is more than 400 members strong and growing. Together, we continue to evolve and improve automation technology, enhancing the realm of open connectivity with new and emerging OPC specifications. Specifications that provide vendors with a wide range of flexible, standardized tools for off-the-shelf products, products for those building with toolkits, and products for those creating entire applications. To date, it's resulted in the development of more than 1,500 vendor products by OPC Foundation members. OPC, open connectivity for today and the future. For more information about OPC Classic products, go to our website at opcfoundation.org, where you'll find the OPC Foundation product catalog.
What is OPC? OPC UA is an open standard that specifies information exchange for industrial communication, particularly on devices within machines, between machines, and from machines to systems in a convergence of IT and OT. It can be used with any software platform, Windows, Linux, Mac, Android, well, you get the picture. And this makes OPC UA scalable. From minimal embedded controllers to massive cloud infrastructures, even mobile devices. OPC UA is equally suited in a closed network or utilized via the internet. Don't worry though, security is baked into the protocol for access control, authentication, and encryption. Because of its flexibility, OPC UA has been widely adopted in industries like automotive, food and beverage, oil and gas, energy and utilities, packaging, building automation, and so on. So, as manufacturing moves into the Industrial Internet of Things Industry 4.0 realm, OPC UA is already poised to fulfill the requirements.
Remember to open your ports if you're using a software-based PLC and HMIs. We're going to cover some of the most popular field buses in the book. We have 16 pages dedicated to just networking and industrial networking, and we show all the ins and outs of these different networks, how they communicate, the different protocols they use, what their baud rates are, typical distances and voltages. These are all referenced in the book, the CSE exam reference manual. And we cover, like, if they talk something about a layer, what layers a certain protocol's on. And in field buses, typically some of the layers are combined. Might have layer 2, 3, and 4 combined, or it may actually skip certain layers as it comes down to OSI model. So it's not really that important for the exam, so I wouldn't worry about it. Okay, when you're setting up these Cisco and Rockwell switches, the Stratix 5800, 5700s, and the IE 2000 and 3000s, never hit the express setup. It'll totally mess you up. It'll put in some kind of a weird address like 204 dot something, and it won't work. What you do is you get your computer, your laptop, you get a patch cable, and you set your computer up for a dynamic host connection protocol. And then you press the button on the industrial switch. It has a dynamic host connection protocol server. And whichever port is flashing, that's the one you plug your cable, your patch cord into, typically port 1. And only the one flashing. Only when it's flashing do you plug in. Then once you're plugged in, it turns solid green. and it'll give you a dynamic host connection IP address, and then you'll start your browser, and it'll pop up the dialog you're seeing now. And this is where you put in your IP address, either static or dynamic host connection protocol. And typically we're going to want static IP address for our switch so we can reach it and do administration on it later. Also put in your default gateway. That'll be the gateway to the router to get out of the network. And you'll want to put in a new password. Be sure to check your subnet mask and make sure it's correct as well. The other thing I want to talk about is in the specification, talk about crosstalk. We talked about this in the specifications. Crosstalk is just where you have voltage interference going into the transmit and receive, and it causes corrupted data. And so you just have to resend it with this crosstalk. And this can be done by the lines. It can be done by EMF or RFI from radio frequencies around you. In wireless, it can be done because there's too much congestion on the same channel. So if you're having problems with wireless communicating and you keep dropping packets, the thing to do is to change to another channel. Also, they're talking about parity. And parity is how many bits you're using. And typically this is on a serial connection where you're trying to hook a serial connection up to a PLC to program it. And it's used with error checking. And you set it for either even, odd, or none. And depending on the error, it'll do an algorithm to check the bits and make sure that the checksum is either even or odd, or you can say none. So they'll talk about the parity, and they'll talk about the error checking, and this will be like cycle redundancy check, or BCC. We've pretty much covered the specifications now. I think it's good enough for this review. Just get the book and read the chapter on industrial networks. I think it'll have most of the information you need for the exam. I'll be sure to familiarize myself with that before taking the CSE anyway. That's it. I guess we're out of here, and I'll see you in the next video. Bye.